Okay, so in the last day before we test Chapter 7 and Chapter X, does anybody have any questions about either review? We could go over, if nobody has any questions, maybe I'll just pick a couple and do them with you myself.
I have a question.
Okay, which one do you want?
Number 1 of the Chapter 7 review.
Okay, so number 1. So do you want to do A, or you want me to go through A or B with you?
1. The first one.
The very first one. Okay, so 1A. All right, so we're going to graph those two equations and see where they meet, because where they meet is the solution, right? So the easiest way, I think, to graph a straight line is to change it into the form we learned about last unit, the form we call y equals mx plus b, or also we call it slope-intercept, right? Because the m is the slope and the b is the y-intercept. So if I take the first equation, I'll minus x and I'll minus 1 from both sides of the equation, right? Then I don't want to know what negative 1y is. I want to know what y is. So I'll divide both sides of the equation by negative 1. And there's my first equation. It has a y-intercept of 1, and it has a slope. Remember that the number here, that m number, is 1 over 1. So rise 1, run 1. Rise 1, run 1. Rise 1, run 1. And now I'm going to take a ruler, try to do this fairly accurately. Oh, even with a ruler, I can't seem to hit dots. And now it's not letting me write. I keep hitting it too high. Okay, this is the one. This is the one I can feel it. This will be the good one. That'll do. Okay, so there's the first equation. I'll do the next one in green. In green, this one's even easier to turn into that form because it's almost there. All I have to do is divide both sides of the equation by negative 9, and then we're in this form. So y would equal 6 over negative 9x plus 36 over negative 9, and then I'm going to simplify that a little. First of all, the negative can go on the top or the bottom. I'll put it on the top. It's easier that way. And that simplifies to 2/3. And 36 divided by negative 9 is negative 4. So we have a y-intercept of negative 4, and my slope is negative 2 over 3. So actually, you know what? I'm going to actually change my mind. I'm going to put that negative on the bottom. So remember that this number is my rise, and this number is my run. So rise 2, run backwards 3. And there it is. I think we found our winning spot. Our solution is the point negative 3, negative 2. So that's my solution. We found it by graphing. That's where they meet. Now, we're going to verify this. We're going to verify both equations because it's asking me to. So on the left-hand side of this equation, if I plug in negative 3 and negative 2, I'm going to get negative 3 minus negative 2 plus 1. And this side's 0. And both of those are true. So yes, that one works. Let's try the other equation. If y is negative 2, I have negative 9 times negative 2 on the left-hand side. And on the right-hand side, I have 6 times negative 3 plus 36. 6 times negative 3 plus 36. So this time I actually do have to simplify both sides. Negative 9 times negative 2 is 18. 6 times negative 3 is negative 18. But when I plus negative 18 and 36, I get 18. So both sides are the same. So verified. Both equations have that point in them. So that's how I do that. So why don't you take a look at the way I just did 1A and see if you can do 1B the same way. I have a question here that says, if there are graphs on the test and we do the test on a piece of paper, what you do? Oh, I was explaining at the beginning that rather than making you draw out grids, I am going to test these types of questions using multiple choice. So that will be on the EDSB part of the test. You weren't here when we did the last chapter. The last chapter we didn't graph lines together and see where they met, but we had a test where at least 15, maybe 20 of the marks of the test was involved having the ability to either graph lines or read what the equation is from the graph of a line. So I don't feel as though if you aren't actually drawing graphs, you're losing out on anything on this test. So the pictures will already be there. You have to interpret them. You won't actually be drawing graphs on this test. Does that make sense? Okay, so that was the first question from Chapter 7. Anything else from the Chapter 7 review? Or else maybe I'll just pick one more substitution and one more elimination. And then we'll move on. Anybody got any that they tried that they couldn't get the same answer as my answer key? Okay, I will pick one then. I'll pick, let's see, so this one's substitution. That one's substitution. I'm going to do 3. I'll do number 3. So my substitution, you know what, I'll even approach it a couple of different ways. Check this out. How about I'll do this one by substitution, and since this one's already y, I'll change this equation a little so that it's y equals 5 minus 4x. I'll minus 4x from both sides. Then I'll replace the y in this equation with 5 minus 4x. And now I have the kind of algebra I learned how to solve in grade 9. Oh, somebody's actually requesting number 2? Okay, I'll go back to number 2 in a second. All right, so now I'm going to go 2x minus 20 plus 16x equals 7. 2x and 16x is 18x. Add 20 to both sides, and I get 18x equals 27, which means that x is equal to 27/18. Now, you should be able to notice that simplifies. Both of those numbers have a 9 in them, so that's 3/2. And no, I don't want decimals. I'm kind of happier with the fraction. Okay, so that's the answer for x. For y, one of the good things about the substitution method is you're kind of set up to substitute back in the other variable. So instead of x, I know that x is 3/2. Replace that x with 3/2. And 2 goes into 4 twice. So this is 5 minus 6, which is -1. So my answer is 3/2, comma, -1. And if I have the time, it doesn't say I have to verify. If the test doesn't say verify, I think there's actually only one question that's going to make you show me a verify. But if you have the time, you can check your answer. Since I used this equation in this step, I'll go back to the other equation to check the answer. So does 2 times 3/2 minus 4 times -1 make 7? If this isn't a true statement, I've got the wrong answer. 2 goes into itself once, so that's 3. 4 times -1 is +4, and that looks like a right answer to me. Okay, so there's number 3. We had a request for number 2. Okay, for number 2, you might not have been here when we learned how to do this. We'd rather not work with these big nasty fractions. So we can multiply this entire equation by a number that will cancel all of the fractions in one fell swoop. And that number is 6. So if I times 1/2 by 6, I get 3. If I times 5/6 by x, I get 5. The only problem with this is the numbers are going to get kind of big on me. I am going to unfortunately be stuck with 6 times 24. 6 20s would be 120, and 4 more 6s is 24. So that's 144. Oh, that makes sense, because 6 times 24 is like saying 6 times 2 times 12, which is 12 times 12. There we go. And now this equation, I can make the fractions go away if I multiply by an 8. So if I multiply by an 8, that'll cancel the 4, but leave behind a 2, so 6x. And if I multiply an 8th by 8, I get 1. And if I multiply 3 by 8, I get 24. Now this one's nicely set up again for substitution because y doesn't have a coefficient, or it has a coefficient of 1. So I'm just going to rewrite this as y is equal to 24 minus 6x. And then I'm going to replace this y with 24 minus 6x. And then I'm going to expand the bracket. 20 times 5 is 100, so that's 120. A negative times a negative, don't forget that that's a positive. That's a super easy mistake to make when you're doing this stuff. 3x's plus 30 is 33x's. And right here I could notice that actually all 3 of these numbers are divisible by 3. make my life a little easier. How many? 40, right? And, ooh, how many 3s in 144? 3 goes into 12 4 times with a 2 left over, 48. There we go. And then last step, I'll add 40 to both sides, or last 2 steps. I'll add 40 to both sides, giving me 88, and 88 divided by 11 is 8. So x is 8. Plug that x right up there. And y is 24 minus 48, which is negative 24. And then you could do a check to make sure that that's the right answer, but seemed to be working out pretty good. I bet it works. Any questions on how I did this? Now, that's one way to do it. You want to see a fancier way to do it? Ooh, this is kind of fun. I decided to substitute y because I saw this y was easy to kind of isolate. Check this out. How about I take this equation? Ooh, this is fun. I like doing this. Take this equation. If you don't think this is fun, we can't be friends because this is fun stuff. I'll simplify it for 3x. I'll isolate 3x. And then in this equation, you know what 6x is? 6x is 2 times 3x. Do you agree with that statement? 6x is 2 times 3x. So since 3x equals 5y plus 144, I can replace this 3x with 5y plus 144. And then that's going to be 10y plus 288 plus another y is equal to 24. I'm going to minus or add those together and get 11y. I'm going to minus 288 from both sides, giving me negative 264. And 11 does go into 264 because 11 goes into 26 2 times with a 4 left over, and 11 goes into 44 4 times. So, yep. I'm getting the same answer. I kind of like that way better. But I realize that this is maybe a little more thinking than some people want to do. So there's a couple different ways you could substitute and get number 2. Is there any steps in here you want me to elaborate on? I'll give you a second to kind of take that in. Let's see if I can find my beverage. There we go. All right. All right, anybody else? So that was a substitution one. Let's do an elimination one. Okay, if it'll say right on the test tomorrow that if you don't do the question in the method it tells you to use, you won't get marks. So you have to do what it says. So here's an elimination. Let's use one. Let's do another fraction one. Is there an elimination? Oh, there's no elimination with fractions. Oh, okay, fine. All right, we'll do this one. This is a very simple, that one's too easy. That's a very simple elimination because you can just add those equations together and boom, you've eliminated y. That one's too easy. There we go. This one's harder. See, if I add those together right now, I won't eliminate anything. I'd still have a y, I'd still have an x. In fact, I'd have 1y and negative 2 x's. So I am going to manipulate these equations so that something will eliminate. I am going to times this equation by 3 and this equation by 4. So that means they'll both have a 12y. Only this one will be positive, this one will be negative. So I can just add the equations together and the y's go away. So 3 times 4y is 12y minus 15x equals 6. 4 times negative 3 is negative 12y. 4 times 3 is 12. And don't forget the oh, look at that, I made a mistake. Okay, where's my mistake? Who can see my mistake?
The 6.
Yeah, that should not be a 6. That should be 3 times 6. There. And then on the bottom one, 4 times negative 4 is negative 16. There. I can add these together now. Those 12 y's, positive and negative, they eliminate one another. Negative 15 plus 12 is negative 3. And 18 minus 16 is positive 2. So this one ends up being kind of a nasty fraction. Ooh. Is this what you guys got? Blech. Okay. Oh well. We ain't afraid of no fractions. We're going to take this answer and we're going to plug it into here, to the x. So 4y minus 5 times negative 2/3 is equal to 6. And we can multiply that out, 4y. When you times together two negatives, you get a positive. And remember, this is like saying 5 over 1, right? So 5 times 2 is 10. 1 times 3 is 3. Then I'm going to minus 10/3 from both sides of the equation. If I'm going to minus thirds from 6, I better turn 6 over 1 into 18/3. And I'll continue over here. So 4y is equal to 8/3, right? And then I'm going to divide both sides of the equation by 4. But remember, when you're in fraction land, you never think divide. You think multiply by the reciprocal, right? That's the same thing as dividing by 4. Okay? So 4 goes into 8 twice, and y is positive 2/3. So I think that the answer, the solution is negative 2/3 for x and 2/3 for y. And yep, sometimes the answers turn out to be oogly. I mean, that's not too bad. That's a pretty simple fraction. And it would be even simpler if I plugged it into this equation as a check, because notice when you times by 3 on both the x and the y, those denominators go away. So to do a check on this one's super easy. Negative 3 times the y, which is 2/3, plus 3 times the x, which is negative 2/3, should equal negative 4. 3's cancel. And yeah, I have negative 2 minus 2 is negative 4. Yep, we is correct. The verify worked. So that's how I would do 4. So whoever was asking about 4, is there any steps in there where I lost you? Is that the only way to do it? Nope. Notice I made the decision to multiply by 3 and 4. I could have made the decision to multiply the top equation by 3 and the bottom equation by 5, and then I would have eliminated the x's and solved the y's. That would work. Feel free to try that. If you were stuck on this question, now that you've seen me do it, why don't you try it the other way? You should get the same answer. Try multiplying this equation by 3 and try multiplying that equation by 5. And then those guys will eliminate, because they'll both, one will be negative 15x, the other one will be plus 15x. Okay? So who was asking about 4? Okay, there you are. Yeah. Okay? All right. There was a substitution. There was an elimination. How'd the word problems go? Let's pick one of them. Let's do the B one. Evan's school is selling tickets to the production of High School Musical. Yeesh. On the first day of ticket sales, the school sold 7 adult tickets and 12 children's tickets for a total of $148. The school took in $98 in the second day by selling 7 adult tickets and 7 child tickets. And I think what we're going to say is, what is the price of each one? So I'm going to let x equal price, that's an x. Let x equal the price of a child ticket. And I'm going to let y equal the price of an adult ticket. So if I sell them for x each, and there's 12 of them, 12 child tickets will earn me $12x, and 7 adult tickets will earn me $7y, and I know that that's a total of 148. The next day, it was 7 of each of them, and it earned me 98. And that one's nicely set up for elimination. All I have to do is subtract, and y's go bye-bye. 12 minus 7 is 5. 8 minus 8 is 0. 14 minus 9 is 5. And I has 10. So then I'll go back to, say, the first equation, and if x is 10, 120 is 12 times x. I'll minus 120 from both sides, giving me 28. Divide both sides by 7, and there it is. Therefore, yes, you need a therefore, and you need a sentence. Child tickets are $10. Adult tickets are... No, wait a minute. I got that backwards. Oh, no, I don't. Whoa, that's weird. Right? 12 child, 12x. 7 adult, 7y, and 7... Yeah. Very few places in life are the children more expensive than adults when you're buying tickets. But that's the way this problem works. Counterintuitive. But there we go. Yeah, you should get the same 2 equations, and you should get the same result, because you just defined yours differently than mine. You should get the same result, though. Okay, I have a request for 6C. Let's see, what's this question? I don't even know what question. Oh, this is 6. This is 6B. 6C, okay. So Robbie has been saving dimes and quarters to buy a new toy. She has a total of 42 dimes and quarters. So, okay, I'm going to let X equal number of dimes. And I'm going to let Y equal number of quarters. And the easy equation is the second piece of information. Or no, sorry, the easy equation is the first piece of equation. She has 42 of both. I don't know how much of each she has, but I know when I add them together, I get 42 coins, right? Now, that one's how many coins. The next equation is going to be value. Every dime is worth 10 cents. And every quarter is worth 25 cents. And together you get $6.90. And I don't know about you, but I don't think I would really want to work with decimals like this. So I would probably, this would be me, I'd probably multiply this equation here by 10. So I get 10x plus 25, oh, sorry, did I say 10? I meant to say 100. 10x plus 25y is equal to 690. Then I might even I could even divide this equation by 5 because everything here is divisible by 5. Or I could just now times this equation by 5 and then subtract them. You can probably handle it from there, right? The tough part was getting these two equations. Okay. The person who shall not be named, I don't know what you're talking about with the 4 and the 12. And 4 and 12. What do you mean 4 and 4? Oh, I see. It's a pun. I see. Get it. Okay. Sorry. Didn't see your 12, your pun for there for a second. Okay. I think that pretty much exhausts the chapter 7 review. Right? Unless you want to talk about one of these. How are you on this stuff? Right? How many solutions does this have? You can approach these. There's a couple different ways you can approach it. Remember that if the slope is the same and the y-intercept's the same, well, then it's the same line, infinite solutions. So you can change these into y equals mx plus b, and if they have the same m and the same b, infinite solutions. If they have the same m but a different b, well, then they are parallel. They have no solutions. They'll never meet. And if they have a different m, you don't even have to worry about b. There's only one solution because straight lines can only cross each other once. So that's one way to do it. The other way to do it is to actually just approach it like algebra. And remember that if you end up with a statement like 0 equals 0, well then congratulations, you had the same line twice, infinite solutions. If you end up with something goofy like 0 equals 7, both of the variables cancel but the other side still has a constant, well then that means no solutions because you've hit parallel lines. And if it solves, then obviously you have a solution. I haven't understood the C. Are you talking about this C here? Is this the C you were asking about? Okay. Possibly, you being somewhat new to us here in Canada, you're probably stuck a little bit with the concept of dime and quarter, right? That's money, right? So the second equation, a dime is a coin. It's got a little boat on one side and the queen's head on the other, and it's worth 10 cents. So if I have one of them, that'd be 10 cents. If I had two of them, it'd be 20 cents. If I had three of them, it'd be 30 cents. So however many I have gets times by 10 cents, and that's how much money value I have. Quarters are literally, like it says, a quarter of a dollar. So 25 cents per coin. So if I had one of them, it's 25 cents. If I had two of them, it's 50 cents. If I had three of them, 75. Four of them, $1. So however many I have times 25 cents is how much they're worth. And it tells me that the worth of all my coins is $6.90. So basically, again, I came up with an equation for total number of coins and an equation for the total value in money. So that's how I set that one up. Okay? We actually took it, or I took it. You know what? I honestly don't know how other teachers are testing this unit. I kind of went rogue on this one. Like, I do things my way. I'm kind of taking it easy on you in this test. There's actually only going to be one word problem where you have to come up with the equations yourselves, and I'll give you two to choose from. So you'll read them, and then you'll go, oh, I understand that one better than this one, and then that's the one you'll do. No, I won't give you bonus marks for doing them both, so don't do that. Okay? So you'll read the equations, or you'll read the word problems, you'll pick one that makes the most sense to you, and you'll solve it. And by solve it, I mean you'll do what I did here. Here's a complete one up here, B, right? You give me let statements. If it's geometry, you could give me a diagram, but one way or the other, you have to tell me what x and y means. You set up equations, you solve them, you give me a therefore. Of the 4 marks, this will cost, this and this are 1 mark. You get a half mark just for let statements and therefores. It's like I'm teaching you English, I'm giving you a half a mark for a sentence. Okay. In the top equation is multiplied by 10, it'll be $420. No. Yes, it would. Well, yeah. So I would take 10, 10, so that'd be 10x plus 10y equals 420, and then I'd subtract the equations, right? So that'd be 15y is equal to 0.72, and 15 does go into 27 because 15 has a 5 in it, that's a 0, so that has a 5 in it, and 3 goes into them both, so yeah. 15 goes into 270, I don't know how many times, I'd have to think about it. 15 goes into 90 6 times, so is that 18? Somebody double check my mental math. That might be wrong. That's just very quick mental math. Okay, anything else from the Chapter 7 review? All right, let's move on. How'd the Chapter X review go? The test is like 30 marks or so of Chapter 7, and then there's only 6 marks of Chapter X. So Chapter X is a bit of an afterthought. Oh, it's so much of an afterthought, in fact. Hey, guys, you got your Chapter 4 book on you? Did I accidentally send you and give you the version of the Chapter 4 book that has Chapter X at the end again? Because I think I did. Because when I put it onto my OneNote here, it's like, oh, drat. I think I've got the Chapter X on here. I have a version of this book that's only Chapter 4, and that's the one I meant to send to the printer for you. But I don't remember what I did. Yeah, look at that. I probably have Chapter X at the end of your book, don't I? Rats. Well, rats. Well, we killed a tree. Sorry about that. Gave you some extra pages you didn't need. All right, so anyway, Chapter X is minor. It's 2 little formulas, can you use them? And 1 type of problem to solve. And it kind of is an algebra problem, which is why this is kind of a good thing to put in the algebra unit. And that is, what happens if I give you the end point and the midpoint, and you have to find the other point? Is there anybody who needs any help with Chapter X stuff? Anybody? Anybody? Somebody's leaving. Who told you to leave? Somebody left. Anyway, anybody? Chapter X, we good? Again, it's 6 marks. I'll guarantee you'll get 1 where you have to use the distance formula. You'll get 1 where you have to use the midpoint formula. You'll get 1 where you have to solve for an endpoint given the midpoint. And yes, we give you the formulas will be on the front page. You don't have to memorize formulas in this course. Okay, I think I'm Chapter 7'd out. I can't wait to be done with this Chapter 7. We've been doing this a long time, it feels like. We spend too much time on Chapter 7. I am so looking forward to Chapter 4. So why don't we spend a few minutes talking about Chapter 4? If you go now into that big pile of books I gave you, remember that day that I just stacked books onto your table? You should be able to find this book. And again, my apologies, it has some pages at the end that you absolutely don't need because we already did them. But this is the chart that I want to talk about today. We're going to have some fun with this chart. I love this chart. This is one of my favorite pages of the whole course right here. We've sort of talked about this a little bit before. This has popped up before. But these are the sets of numbers that you, as a grade 10 student heading into pre-cal or applied math, should be familiar with. If you're heading into essential math next year, it doesn't really matter that you don't know the difference between different sets of numbers. But here in the pre-cal and applied programs, it needs to make sense to you what types of numbers you're dealing with. And natural numbers can be defined as the set of all counting numbers. And the symbol we use for natural numbers is a capital N, usually it has a little extra line on there. And for example, 1, 2, 3, 4, to forever, to infinity and beyond. It is an infinite set, right? You can count, excuse me, you can count forever. It's an infinite set of numbers. Now, whole numbers, there are some places, our friend who was just in Europe doing school, again, I don't say people's names when I'm recording a video, so if I say your name, I've made a mistake. But our new student who joins us from France, I don't think they have, in fact, I know this for a fact, in French, they don't have a word for whole number. Here in Canada, for our French students in Canada, they'll say naturel avec zéro, which kind of makes sense, right? Because that's what this set is. It's the set of all counting numbers including 0. You don't need 0 to count with, right? Roman numerals existed without 0, and math was around for thousands and thousands of years before somebody finally decided, we should include like nothing as a number. So 0 is not necessary to count with, but boy, it makes life a lot easier to count when you have 0. You can start at 0 and go 0, 1, 2, 3, and we call those whole numbers, or again, en français, naturel avec zéro. And there used to be a grade 9 provincial exam, and I used to be on the committee that made that exam, or made up the questions for that exam. And every year, I would try to think of a question that you could ask that the French could answer. Because in English, it's easy. You say, which of the following numbers is a whole number, but not a natural number? And of course, one of your 4 choices is 0. But notice in French, that wouldn't make sense, because you don't have the word whole. The word whole in French just means, complete, entire. There's no way to ask it. So I was never able to ask that question. Turn on your microphone and you can ask your question. I see you have a hand up.
Yeah. So I'm the French guy, and that's right. We don't have the whole numbers. We
No.
only have the natural
Yeah.
number.
And you know what? I think that Europe is winning this particular fight of ideas, because I've actually seen a couple of American textbooks now. Boy, you know that Europe's onto a good idea when the Americans want to adopt it and think it's a good idea. Usually the Americans are like, what? That's the way Europe's doing it? We'll do it completely opposite. But I've seen some American textbooks now that say that 0 is a natural number. For hundreds of years here on this side of the pond, nope, natural numbers start at 1, because historically, it was the ancient Greeks and the Romans who defined natural number, and they never had 0 as a counting number. They didn't even have it as a placeholder, right? Because they didn't have a base 10 counting system. So yeah, even the Babylonians, right? I think they had like a base 60 counting system. So yeah, 0 has never been a natural number until recently, but certainly Europe has gone that way, and I think the Americans are too. And I have a feeling a few years from now, even the Canadians will start saying, to heck with whole numbers. Why invent the whole set for one extra number? But anyway, as of right now, the curriculum says that these are different sets, but they're only different by one thing. This set's got a 0 in it. That's about all. Integers, of course, is the set of all numbers that can be written without a fractional component. Now you're probably saying, well, isn't that what whole number means? Well, no, because notice all the whole numbers are still positive. Integers is the first set that goes forever in both directions. So dot, 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 and yes, that's a Z with an extra line. Sorry, I drew it so ugly. Dot, 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 -3, -2, -1, 0, 1, 2, 3, dot, dot, dot. And at this point, you'll probably notice a pattern. You'll probably notice that, oh, well, this set here is just the naturals with one more thing added. And, oh, integers is just the whole numbers, but I add all the negatives. But be careful. I'm only adding whole negatives to the set. The number -1/2, that's not an integer, because I can't express 1/2 without a fractional part. You might be saying, well, you could call it 0.5. That's still a fractional part to me. So negative decimals and negative fractions don't belong in integers, nor do positive integers and let me say that again. Neither do positive fractions and positive decimals. This is all whole amounts. It just goes into positives and negatives. And that's what we call the integers. That, of course, is where we can talk about the very famous, and I think we had this, I think I said this story earlier in the year. I should have saved it for now because it kind of makes more sense to talk about it here. But this is where we can talk about the Hilbert Hotel. And the Hilbert Hotel is this grand hotel that has an infinite number of rooms. And they're numbered. This is room 1, room 2, room 3, room 4, room 5. But of course, it's infinite because you can count to infinity. And of course, then, let's say that there's a convention in town, there's a number convention in town, and all the numbers show up and they all want to stay in the Hilbert Hotel. So the bellhop goes, oh, okay, no problem. Number 1, we'll put you into room 1. Number 2, we'll put you into room 2. Number 3, we'll put you into room 3, and so on. And that's how it's going to work. And then everybody's in their rooms, everybody's happy, and content for the night. And then, wouldn't you know it, in comes trouble. 0 shows up. Where do we say, sorry, 0, but the hotel's full? The hotel has infinite rooms, so it's not a problem. We just say, we'll take everybody who is in room N, and we'll tell them to move to room N plus 1. So if you were number 1, you just move to room 1 plus 1, which is 2. If you were in room 2, we just move you to 2 plus 1, which puts you in room 3, which would leave 0, a nice empty room in room 1. No problem. That's how infinity works. 0's got a place to stay. So everything's fine. Everybody's happy. Then in rolls an infinitely big bus. This is a number convention, of course. And you know who shows up for the number convention? All of the rational numbers show up. All of them. Now, what are rational numbers? Well, let's define it. This one's kind of a big definition. You got to do a little bit of writing here. This is the set. I got to write. You know what? I'm going to make it bigger so I can write small. Ooh, that's a good idea. Oh, now I can write super small. Fit this in. Come on, erase. There we go. The set of all numbers that can be expressed as the quotient of 2 integers. That's what rational numbers are. It includes all terminating and all repeating decimals. Actually, I didn't need quite as much space as I thought I would. But there we go. There's the definition of rational numbers. That is, I think, the same definition you had in grade 9. Geez, I only taught grade 9 for 18 years at Acadia and 5 years before that. 23. I only had grade 9 math 23 straight years. 4 years ago when I moved here to FRC, that was the first year I didn't have grade 9 in my career. Reminds me of a little story. When my grandma was close to passing on, she was getting very, very, very sick and old, and we took my kids to go visit her, and they were still pretty little, but you don't tell kids when they're little, but this will probably be the last time you get to visit your grandma. And my grandma was a really nice lady, and she asked my youngest son, she says, And what grade are you going into next year? It's the summer, right? So what grade are you going into next year? And he goes, I'm going into grade 1. And my brother William's going into grade 3. And Ben's going into grade 5. I have 3 sons. Dad's still in grade 9. So sometimes I think it took me 23 years to get out of grade 9. But there you go. Grade 9. Is this do you guys remember this? Is this what it sounded like in grade 9? Anything you can make a fraction out of, or a decimal that terminates or repeats. So I guess we maybe should talk about what that means. What does it mean to terminate? Terminate, of course, means ends. And of course, repeating means in a pattern. I've had students who try to tell me that, well, pi is a repeating decimal. It just keeps on giving me numbers over and over again. Well, that's not what repeating means. Repeating means it has to have a predictable pattern where you'll see the exact same sequence over and over again. Pattern, maybe I'll say that, in a pattern of the same sequence. Okay, so now let me finish the story we were getting to. Oh, actually, first of all, let's do this side of the chart. It should probably make total sense to you what letter we use to represent rational numbers, right? Of course. Yeah, exactly. It's a Q. What do you think it was going to be, an R? Sorry, look down the list. We're going to save R for real numbers. It's a Q. Oh, and again, we're supposed to put an extra line in it. Most of us draw it like this, which is very nice. And now here's the problem, though. Notice how I've made this list in a row. Let's go back to natural numbers. If I kept going and I had infinite time and an infinitely big pencil, because I'm going to wear the lead out, could I write the entire list? And the answer is yes. If I have infinite time, infinite paper, infinite pencil, I can write the entire list. Can I write the entire list of whole numbers? Well, yeah, I just had to start one before, but again, given infinite time, infinite paper, infinite pencil, I can write you every whole number. Could I write every integer? Yes. Again, I'd have to write in 2 directions. I'd have to have infinitely long arms and be ambidextrous, so I could write this way with my right arm and this way with my left arm. But eventually I could make you a list that has every single integer on it and not miss any if I have infinite time and infinite paper and infinite pencil. Could I do that with rational numbers? Notice how hard it is. It's not like I can put them in a row like this. You might be thinking, well, you could kind of put them in a row. You could go dot, dot, dot again, and then you could just pick a place to start, like say -1, and then the number before that would be like -0.9, and then the number before that would be -0.8, which, let's do the fraction, -4/5, and then etc. Let's skip a few, and then you could put a half and 2.78, and if you just had some patience, like I was in a row here. Well, were you really in a row? Is 0.9 for sure the next rational number to the right of -1? Think about a number line. On a number line, here's 0, here's -1. Are you sure there's no rational numbers between -0.9 and -1? Zoom in, dude. There's infinite numbers between there. What about -0.91? What about -0.9001? What about -0.90000001? So the number of rational numbers between any 2 points on my number line is infinite, right? Like again, suppose I said, okay, here's 1, there's a half. Let's do fractions instead of decimals. Well, there we go. There's no fractions between those. 0, a half, 2 halves, 3 halves. Well, what about a quarter? What about an eighth? What about a 16th, a 32nd, a 64th? There's infinity between the points. So surely our bellhop at the Infinite Hotel has a problem. Surely if every single rational number showed up, he'd have to say, we're full. Right? Wrong. He can fit them all. Here's how he's going to do it. He's going to make himself, first of all, he's going to make a chart. He's going to make a chart where he's going to say, all right, I'm going to say that I'm going to, across this row here, I'm going to leave the numerator as 1 and change the denominator. And it's an infinite row. In this column, I'm going to keep the denominator, but change the numerator. So this is 2 over 1, 2 over, 3 over 1, 4 over 1, 5 over 1, 6 over 1. And then I'm just going to keep that pattern going. So as I go down this column, I am 2 over 2, I'm 3 over 2, I'm 4 over 2, 5 over 2, 6 over 2. And as I go across this row, I'm keeping the numerator the same. So that's 3, 4, 5, 6, 7, 8, 9, 10. And then I'm just going to fill this in exactly the way you see it. So this is again, so this, I'm keeping the rows the same. So 3 over 3, 3 over 4, 3 over 5, 3 over 6, 3 over 7, 3 over 8, 3 over 9, 3 over 10. And this is going to be 4 over 3, 4 over 4, 4 over 5, 4 over 6, 4 over 7, 4 over 8, 4 over 9. You get the idea. 5 over 3, 6 over 3, 5 over 4, 6 over 4, 5 over 5, 6 over 5, 5 over 6, 5 over 7. It's actually faster to think this way than it is the other way. Isn't that interesting? I wonder what the mental thing about that is. 6 over 6, 6 over 7, 6 over 8, 6 over 9. Okay, so there we go. So given that my bellhop has infinite time and infinite pencil and infinite paper, he, of course, could make a list of, like this, that would have every single fraction on it. You might be thinking, what about the negatives? Okay, well, he has to make the list twice, and on the second list, he puts all the negatives down. And that would do it. Every single fraction that got off that bus is here somewhere. In fact, well, we'd even have some of them twice. Like 1/2 and 2/4 is really the same fraction, isn't it? But every single possible combination is on here. Now, you might be thinking, well, you're kind of cheating, because certainly you can write a list starting here and go forever. You can start here and go forever. This one, you have to start in the middle and go in 2 directions. But of course, you could write this way. Right? How, if this is a chart forever in 2 directions, how could you have a list of every single number? And the trick is, you count the diagonals. Here's my first number. Then I'd start it here and do the next those 2. Then I'd start here and do those 3. Then I'd start here and do those 4. And if I keep doing the diagonals and I say, okay, you, sir, go into room 1, and you go into room 2, you go into room 3, you go into room 4, you go into room 5, and you're in 6, and you're in 7, you're in 8, and you're in 9, and you're in 10. My bellhop, because he has infinite rooms, can put all of the fractions in his hotel. Isn't that cool? So in other words, even though there's infinite numbers between those 2 numbers, this infinity is the same size as that infinity. And even though this infinity you'd think is twice as big because it has all the negatives, no, it's the same size as this infinity. And you might think, well, this is infinity plus 1. It's got 0. This was infinity. This is bigger now. All 4 of these infinities are the same size. And we call them countable infinities. Natural numbers, whole numbers, integers, and rational numbers are countable infinities. They're all the same size. Isn't that cool? All right. That's kind of mind-blowing. So I'll leave you there with a blown mind. And we'll pick it up. Let's see. So we're testing tomorrow. So Wednesday, we'll pick it up right here. We'll get to what irrational numbers are. And we'll start playing with rational numbers. Because like I said, it includes all terminating and repeating decimals. You might be thinking, hey, where'd the decimals go in this story? Well, please notice they're all here. Like 0.3 repeating's right there. 0.528471 repeating is right there. They're all here someplace. Right? 0.4 is right there. They're all here someplace. But how do you prove that? And how can you use that? How can you recognize what kind of a number you have from its decimal? We'll talk about that next time. So that's where we'll pick up next time. So I'm going to stop my little lesson now that it's been significantly mind-blowing for everybody. And I'll let you go. I'm not assigning any homework tonight. Okay, so bye-bye people watching the video.